Hello students. So today we are going to start a new chapter. The chapter is all about gravitation. Now we have learned so far that in our universe generally we have four kind of forces. Strong force, that is regarded with your nuclear binding energy. Weak force, which is responsible for the radiation from nuclei. We have electromagnetic force, which we will learn in the next sessions, and gravitation. Now, it is there are disputes regarding the origins of gravitations, and so many research is going on still now to find the what you say the laws we know, but the cause of gravitation we don't know. So the origin of gravitation, to find that, we have like so many models. One of the model is your famous Einstein GTR theory, that is the general relativity, where it says that gravitation is not a kind of force, but it's a property of space-time curvature. Whatever, but in this chapter, what we will learn? We will learn the properties of gravitation. That means how the gravity works. So we will learn about gravity, but we know that gravity, the study of gravity was started from before, but it was actually initiated during the time of Newton. So we know that Newton was sitting and the apple falls. When he was sitting under the tree, suddenly one apple fall down, and he was thinking, if the apple is falling down, why not the moon is falling down? So apple is falling down to the ground, but the moon is not falling down to the ground. So why it is happening? So that's why he had developed a telescope, and he was looking at the stars, the planetary objects, meteorites, comets, and he was studying the orbits of those. And basically, to study that, he invented also the integration and geometry. The integration and uh, calculus, like um, differentiation. That means the calculus, the whole calculus part he has discussed then. So the to study the gravity, one more thing we have to talk about. We know that the gravity is a force which is very weak, but it governs the whole planetary system. So this big planets, the stars, everything uh, works under gravity. The gravity is a force of destruction also. Why? Because let's say you have a planet and you have another planet. Because of gravitational force, they attract with each other, so they come together and they collide with each other, and it's gone. But generally, it is not the thing that happens all the time. Rather, they orbit in a binary system. That means they orbits in a elliptical path around each other, and we can see this for our solar system also. We know that all the planets around the sun is rotating. Now, before we talk about Newton's gravitational motion laws, we have to talk about Kepler. It was 1571 to 1640 when Jonathan Kepler has given three laws basically, which describes the planetary motions, and those are called Kepler's law. So the Kepler's law is given by three statements. The first one is every planet or the planetary system works like around uh, rotates in an elliptical path, where in elliptical path we have two epicenters. Okay. Now when you will learn about conic section and geometry, you will learn about this, but basically an elliptical path is having two epicenter. So a planetary objects can rotate in an elliptical path with the position of the star at the center of any of the elliptical path. Any of the epicenter. So the star will be in either one of these epicenters, and the orbit will the planetary system will rotate around it. Okay, so this was the first statement told by Kepler. The next statement was uh, about the motion itself. So the next statement was that when can we we can draw an oval, so I will draw. So if something is rotating in this kind of elliptical path, so we have our star here and we have our planetary objects here, let's say. So this is let's say orbiting in this elliptical path in like this. So we know that when this planet will come to another point like this, it will certainly sweep out. So this was the initial distance and now this is the final distance. So when it is moving, it is sweeping out some of the area under the graph, like under the, what do you say, under this area, like it is sweeping some area, okay, within this orbit. When let's say again, when the planet is here and in the same time it has come here, so basically here also what is happening, it is sweeping out some area, this, so it is sweeping out this much of area. So from P to R it has swept out this much area, and from S to T it has swept out this much area. In both cases, if the time taken is same, then the rate of sweeping the area is constant. That means the dA dt, or you can say delta A by delta T, is always constant. So it is sweeping the same amount of area in unit time. Okay, so this was the second statement. We will solve and we will derive this. We will prove this statement. He was right or not. So this was the statement, and the last statement was that when like this, the object is rotating. So if this is an ellipse, then the time period, so you know that this is the star, let's say this is the star and this object was here, so it is rotating. So the time period ka square is proportional. So time period matlab, that means this whole revolution. Okay, so a complete one revolution is your time period. So the time period square will be proportional to r cube. R is the average distance, you can say, from the star itself. Okay, so this was the third statement. So these three are called Kepler's law. Okay. So the first one is it will rotate in an elliptical orbit, whereas the star of the system will be either of this foci, you can say also foci or focus, also this epicenter you can call foci also. So either of this foci. Okay. The next one is when it is rotating, then the rate of sweeping the area, okay, will be constant. And the last one is the time period square will be proportional to r cube. R is the average distance, because you can see here the distance will not be same. So r is the average distance from the star itself. So this was like the Kepler's law. Now one thing also we will see here, that whenever something is rotating like this, whenever something is rotating, and this is the star itself, like you can say sun, and let's say this is our earth. So whenever it is rotating, you can see that at P point and in R point, these points are different. So when it is coming near to sun, the attraction will increase. So we will come to that, how, like in what way the attraction will increase or decrease. So you can see here the distance is less, whereas this distance is high. So OP is much bigger than OR. So when it will come closer, the speed of this what you say planet will increase automatically, whereas when it is far from this, the speed will be less. So we can also tell that this V is proportional to 1 by R, you can say, like so if my radius, like not radius, if my distance is higher, the speed will be less, and if my distance is lower, the speed will be high. So what we can write that the extreme corner and the, like, so we can say that, yeah, the maximum, let's say this is the maximum, or generally also we can tell, let me tell you the general one. So I can say now the speed at A point by the speed at B point will be the speed at B point by the speed of A point. So this is one observation also we have to remember. Okay. Acha. Now we are coming to some more things, like let me first introduce you the gravitational law, and then we will come to prove these things. Okay, the Kepler's law. Okay, so now we will talk about the Newton's observation. Okay, Newton's law of gravitation. So Newton has told that in this universe all the matter attracts each other. So anyway, like they are small or big, they will obviously attract each other. What was the attraction force? So Newton has told the attraction is always in a straight line. So they will attract each other. So that means if I have this A and this B point, or you can say like this mass MA and this mass MB, if we have, they will attract each other. So MA will give some force AB, and MB also will give some force FBA. So you can also say that these two forces will be same because this attraction is mutual. One more thing, this force, so either of this force is proportional to mass A. So if I increase one of the mass, this will increase. So acha, this F is also proportional to mass B, and this force is inversely proportional to the square of the distance between them. Now whenever we have these three things, okay, and if we combine them, we will have the force is equal to some constant, this we call as G, mass A, mass B by the distance square. Now this is a vector quantity, and this will be r cap because it works in a straight line. So in which direction the r is increasing, it works in that way. Now we know that this force is attractive. So if this is the object and this is one object, so this object, the first object will pull, the next object will also pull. So the force is not pushing one, the force is pulling one, right? So that's why. But if you talk about the r, let's say I'm talking about this object, so I want to find the force of the first one. So the distance will increase this way. So whenever I'm measuring r, the value of r will increase in right side, whereas the force is inward. So that's why we can say the direction is minus g MAMB r square r cap, because of the direction, because it's a attractive force. Okay, but for the value we can directly tell that yeah, F is this. Now we can see here that F is inversely proportional to 1 by r square. This kind of force which works like this is called inverse square law, force under inverse square law. So you can see later on, you will see that the electromagnetic force is also such. So the forces of this kind of forces, like the force of gravitational force, is a inverse square law force. Okay. Acha. One more thing we'll come to know. Okay, that the this kind of force, like gravitational force, is called also a central force. Now we will talk about it later on when we will prove the Kepler's law. Okay. Acha. So now let me talk about this. We know that the force is mass into acceleration according to the Newton only. So this is the law of motion and this is the gravitational law. Okay. So this is the observation and this is a model given by Newton. So if force is equal to mass into acceleration, and if we just combine them, so what we can get? So let me take two objects. So this is my mass A and this is my mass B. So mass A is attracting mass B. Mass B is also attracting mass A. But we are just right now considering the force given by mass A to mass B. So what we can do here, we can write down that we can write down the force is equal to G into mass A upon mass B by the distance r square. Now instead of force I can write mass into acceleration. Now who is having the force? So if this MA is attracting or pulling mass B, so the mass B will come closer to this. So if somebody is there on this object mass A, let's say I have fixed it in the somewhere, I have just locked it, so it will not move, whereas your mass B will move. So the acceleration will be there upon this mass B. So the acceleration will be AB. AA will not have the acceleration because I have fixed it. So this will be, so whose acceleration? Mass B acceleration. So that means it will be mass B into the acceleration of mass B. So upon cancellation we can get that the acceleration of mass B is gma by r square. Okay. So in a similar way you can see this one. So in a similar way we can say that if we have the earth itself, big Earth having a mass m, big M, and I have one very small object, small m, uh, above Earth. So the Earth will attract this. So the gravitational acceleration will be in this case. So similarly, this formula. So let's say the g is the acceleration on of this body. So g will be g. Then your ma will become here small m or big M, big M. Why? Because in this case this is ma. So ma means the fixed one. So Earth is the fixed one in this case. So gm by the distance, this distance, r square. This is called gravitational acceleration. Acha, I have forgotten to tell you about the g. This g is an universal constant. Okay, so the value of this g will never change ever. So the value is like this, 10 to the power 11 in order, and then usual what you say, the units are there. Okay, so it will be Newton meter square by kg square. Okay, acha. So this g is like that. So till now we have done till gravitational acceleration. So we have seen that the gravity is an attractive force. It always pull. It does not pull. Does not push. It always pulls. And we have also learned about Kepler's law. So more we will go and study about Newton's law of gravitation. We will also be able to prove these laws. Okay. Acha. So in our next class we will be discussing about this thing, and then we'll also prove the Kepler's law even. Okay. Okay. So for this class, this much is there. I will give you some assignments. Please try to do so, and do read the book. Okay. So see you in the next class. Bye bye for now.